Hello, welcome to adding 0.1 to numbers using calculus by me, John York. So it's going to use something called neural networks, and let me try and explain what a neural network is before we go further. Yeah, that's a neural network. Got it? It seems super complicated. It's not that complicated. Like, there's a lot here. You can ignore most of it. It's just a function. It takes an input, gives output. It's very loosely resembled based on how our brains work because you can kind of see like the neurons kind of all connect together in some way. But it's really just a math function. That's all you need to know. Um, let's see. Let me show you what this function actually is. Um, Here it is. This is literally the function sigmoid of input blah blah blah. Um, what happens? This is a visual of it. I think it's a little nicer. You give it an input at this. It's called input layer neuron. In this case, it's just our input neuron because there's not multiple, but there can be multiple. But for us, it'll just be one. You give it input. It's multiplied by the weight. Uh, there's weights and biases in this network, and what you need to know about them, you can see how they work here. Biases are added, weights are multiplied, but they're just constants. Um, in order for the network to learn, we're going to adjust these, but they are just constants right now. So you have your input multiplied by weight 0, add bias 0, sigmoid, multiply by weight 1, add bias 1, sigmoid. And I've been saying sigmoid like you know what it is, but I'll show you what it is. Um, Not super duper important, but it's just a function that keeps numbers in between 0 and 1. You don't really want numbers getting too big or going negative because that kind of screws everything up, especially in a network where you have like 500 input neurons or 500 neurons in the second layer here. It just wouldn't work very well. But this squashes numbers in between 0 and 1, which is just useful. So let me just take you through an example of passing in 0.5. Pretty simple, relatively. Also, I've defined weights, my weights and biases here. I've just randomly selected some values. I chose 0 0.8, 0 0.2, and biases negative 0.5 and 1. It's not important what I chose them to be. It's just literally random numbers. It's like when you're first born, you don't have anything in your brain. They're just random connections going on. Maybe it's not. I'm not a biology guy, but just random. Um, and this is just putting in 0.5. You pass through the network, you end up getting 0.749, blah blah blah. Okay. So that's cool. That's like awesome. We can pass in numbers to some function. Okay. But now this is where it gets cool. Let's teach the neural network now. We got to decide what I want to teach it. And I went with the incredible task of teaching it to add 0.1 to numbers. What? Yeah, that's crazy. I'm going to add 0.1 to numbers, and there's nothing you can do about it. Um, it's actually a relatively hard task for a neural network to learn because of all the multiplying and the sigmoid, especially here, because it squashes numbers and you lose like precision. Um, but I think my little network can do it. It's also hard because it's a very small network. Like if this was like a massive network, you could get it perfectly instantly, but we've only got two neurons to work with, like this one and this one really. Um, but I've created a data set here. It's what you'd expect. Input 0.1, get 0.2 as our expected output. It's kind of like, I don't know, a math teacher like gives you a problem, 3 times 3. The expected output is 9. Um, and the math teacher will kind of teach you, like, if you get it wrong, you got it wrong by this much, so your answer needs to increase or decrease or whatever. Um, and all the data is what you'd expect. It's just adding 0.1 to numbers. Um, we're gonna also need a function to evaluate how good or bad this neural network is doing. Continuing with my analogy of like the math teacher, it'd be kind of silly if you got a math test back with no grade on it. So you need a grade on your math test to know if you're doing good. You need to study more, or you're doing good. You don't need to study more, or maybe you do need to study more. Um, but this is like the evaluation function that tells us our neural network is like super good at adding 0.1 or like super bad. So 1 would be it's super bad, and 0 is perfect. It added 0.1 exactly. Um, and this is where the kind of the calculus comes in, because this is the function that we're minimizing. We're minimizing how bad our network is, and therefore giving us the best possible network. So defining the cost function, we already know how neural network works. You give it input, it gives us output. Done. This is the cost function. It just has expected minus passing the neural network input, and it's squared. And just for an example, the cost cost is c. Um, given 0.5 and 0.6, it's just one random data point I chose would end up being 0.0222. So that's pretty close to 0. It's all right. It's not super good. And I mean, it did okay. Like, if you really look at it, it was supposed to take in 0.5, give 0.6, and it took in 0.5 and then gave 0.75-ish, which is pretty close to 0.6, so it's kind of reasonable. But let's look at the data across all of our data points. Um, and you can see it does not very good. It's not very good at all. I'll be just totally honest to my neural network. It's not very smart yet, but we're gonna send it to school. It's gonna learn. He's gonna be a fine scholar. Um, we're minimizing the average cost here, okay? Okay, so let's just take this example and minimizing the cost of just this one data point, point 0.5 being passed in the network. We want to get expected as close to 0.6 as possible. And we want the cost to be 0. So what can we do? We can just like take C prime and set it to 0, and then check the critical X values and the endpoints, and our lives are so easy. Little Frederick the network has learned. Such an angel, right? Wrong. No, you thought it was easy? No, it's never easy, man. Okay, so guess what? We actually have 6 variables that affect the cost. There's the input, expected, weight 0, weight 1, bias 0, bias 1. We don't have control over input or expected, so that means we need to try and adjust weight 0, weight 1, bias 0, bias 1. And these are all just constants, and we can edit them however we want. So how about we just take the cost, since there's 4 weights and biases in total, divide the cost by 4, and then decrease each weight and bias by the cost divided by 4. Pretty logical, right? You're probably thinking, why didn't I think of that right now? Yeah, so smart of you. Wrong! Ha! Got you. So, what do you do if you can't kind of blindly decrease it by a quarter of the cost? You need to figure out how much each weight and bias actually affects the end output of the network. Because each one really affects the network much differently. Like the bias at the end here will have a greater effect than the weight over here. because you see it's just put in here, and it kind of gets sigmoided away and multiplied by a small weight. But the bias is actually pretty impactful. So you can kind of see how each weight and bias really does have a different impact on the network. So what to do? We need an intelligent way to decrease the weights and biases in order to minimize the cost function. So we need to consider how much each weight and bias actually affects the cost function. Or, in other words, the rate of change of the cost function with respect to each weight and bias. And this decreases the cost the fastest. We take the derivative of each weight and bias. We take the derivative of the cost function with respect to each weight and bias, and then we're going to multiply it by this small constant called the learning rate. It has to be a relatively small number because we're going to repeat this process literally thousands of times. Because I mean, think about it again. Like you don't learn something the first time usually. Well, maybe you do. Maybe you're a smart guy, but maybe it takes a couple times. And especially this network, not very smart guy, so it'll take him a couple thousand times for it to get in to his head. But the learning rate is essentially just how fast or slow we want the network to learn. But you gotta be careful. If it learns too fast, it might overshoot and just start getting it wrong. And if it learns too slow, it's never gonna learn, never gonna get to the next chapter. All go, 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 you know? Um, okay. So let's just think of a manual run through here. I define neural network here of our input, the cost function. We can derive everything with respect to each weight and bias. And then in order for this to be one iteration of like learning for the network, each weight and bias is decreased by the derivative of the cost with respect to the weight or bias times the learning rate. And this kind of decreases the cost function the fastest. So conceptually, kind of a little bit of a recap, all the weights and biases are decreased by their derivatives with respect to the cost function times the learning rate. However, this is only for one training example. Remember that our data set has 9 different data points. So in order to train the network to learn the general trend in all the data, we need to run through all the data, calculate the derivatives, sum them, and then update the weights and biases so that it doesn't learn just one thing at a time. You're kind of showing it a bunch of examples, and then it takes it all in at once. Um, this prevents it from like seeing an example that makes its weights and biases move this much, and then another that makes it move this much, and then they just keep moving back and forth, back and forth, back and forth, and never really learns anything. Um, this process does get repeated multiple times, so it's a little bit like Newton's method, I was thinking. Newton's method is an iterative process in order to find a zero for a function. Um, so training a neural network is iterative. You calculate the derivatives of the network for that training example, then decrease the weights and biases respectively to their derivatives, and then repeat again and again and again, and eventually your cost function will approach zero. It's very similar to Newton's method of drawing a tangent point on the graph, adjusting your x value based on the zero of that tangent, and then repeating at the next point. It gets very close to zero of that function, of that initial function. It never quite touches zero, I don't believe, unless there's some weird edge cases. Um, there's a little more nuance here because there's 4 weights and biases in total, and you've got your input and your expected. Um, so you'll see a little later that it's not like super smooth going right to the zero. But it is approaching that zero, but it's kind of like you're drawing a tangent in 6 dimensions because it's your 6 variables that affect the cost. Um, okay, let's send our neural network to the dojo. Let's let it learn a little bit. I prepared some beautiful code. I hope you guys like it. I think it's beautiful. Okay. I'm not gonna really explain it, to be honest, because I don't think it really gets much done. Um, it has some good output though. This code here, this is really the big one that learns. Um, I give it 10,000 examples of a random number 0 to 0.9, and then I grade it based on how close it is to that number plus 0.1. Pretty much what you expected. And then instead of updating the weights and biases after each one, I do 50 of them, and then I update the weights and biases so I don't get in that problem of going that I was talking about. Okay, let's run this, and you'll be able to see the cost function does really decrease, but that's not very fun. I'll show you the fun one later in just 1 minute. Um, After it's learned, I could have had a okay. After it's learned, you can see this is pretty good. Let's go to our initial example of zero point 0.5 and learn that it's 0.626. That's very close. That's very good. I learned zero point 0.4 is 0.49. Very good. Good job, Freddie. 0.8, 0.89. Yeah, this is all very good. And then this one is cool. This is a graph. It'll be the cost over time as the network learns. And this is what I was talking about. There's a lot of up and down. It could be more smooth if the learning rate was changed. I'll actually run through it one more time with changing the learning rate, and you'll see that it's a lot more smooth, but it'll learn a lot slower. And I had some fun here, and I just ran through, and this is how much each weight and bias changed as it learned. It's a little interesting. Take it how you will. Um, really quickly, I'll just go and change the learning rate to 1/10 of the previous learning rate and run it again. Yeah, you can see it's a little more smooth. It's definitely learning a lot slower because you're just adjusting the weights and biases by a much smaller amount each iteration. So of course it's gonna go slower. Um, I yeah, let's move back into here. That was pretty cool, right? So, but at the end of the day, what did we do? We added 0.1 to a number, and I spent hours on this. Why did I spend hours to add 0.1 to a number? I do not know. But let's talk about the actual real world relevance of this topic, which is training neural networks. So like kind of like the basic thing that people do after learning how neural networks work is write a program to recognize handwritten digits. There's a beautiful data set called the MNIST data set um, that has 40,000 handwritten images encoded as numbers, which you can use to train a neural network. So it does the same thing. It sees these images who knows how many times, lots and lots of times, because it's a very complicated task. It takes a very large network, not our one, two neuron network, probably a couple thousand neuron network. Um, and it sees these images multiple times, lots of times, and eventually gets a trend, and it's able to then, after it's been trained, recognize images that it had seen previously. And the US Post Office uses a similar system in order to read addresses from envelopes. That's pretty cool. Other real world relevance could be medical diagnosis, social media feed recommendations, Netflix movie recommendations, financial predictions. Essentially, anything that can be quantified and has an observable trend can be learned by a neural network. Even things that don't have observable trends to humans, maybe, but a neural network living in the world of numbers, maybe it could pick up on that trend. And then it could be applied to lots and lots of situations. And just for the record, no, ChatGPT does not use neural networks. It uses some other completely different architecture. It might use a similar concept to backpropagate. This training a neural network is really called backpropagation, but I'd prefer to just call it training a neural network. Um, but ChatGPT, I do not know how it works, but I know it does not use neural networks like this. Anyways, thank you for watching. I hope you really enjoyed